The second challenge is called Split, and in this challenge we have all the elements that allowed us to complete the Return to Win challenge, but they've been split apart and we need to find them and recombine them using a short ROP chain. So it says here that the string bincat flag.txt is still present in the binary, as is the call to system. It's just a case of us chaining them together. So in the previous example we just had to find the address of a function called ret2win, which would call system with this string in it, and if we could find that address and overflow the buffer and overwrite the return address, the instruction pointer with the return address of that function, we would get our flag. So this time it's not going to be quite so easy. We have this string and we have this call to system, but they're not just in a function that we can just call to get the flag. So let's have a look at the binary. We'll have a look at the 32-bit binary first, and again if we just check sec and have a look, we can see that no execute is enabled, so we can't just place code onto the stack to execute we can't just place our own shellcode to execute, but we don't have any other protections on there. We can also have a look with Rabin2 again, -z, and have a look at the strings. So we know that the string is in here. We also have the address of the string, and then we can see some other information about the user prompt and stuff like that. We also have this bin/ls command in there as well. We could also have a look at the functions, rabin2-i split, and we can see that the system function is indeed in there. Rather than disassembling this and looking through the functions in pwntools as we did previously, or in radair2, I'm going to introduce CommandoVM, and we'll have a look at the binary in a visual disassembler called IDA Pro. So CommandoVM isn't something I have a lot of experience with. I hope to gain some more and maybe do some videos on it in future, but it's essentially like a Windows equivalent of Kali Linux. You can download this, you can go to the GitHub and run a script, and it will essentially install a Windows 10 VM. It'll configure everything for you, go through and remove all the necessary stuff and make a lot of changes to the system that would take a long time to do manually, not to mention the tools. As you can see here, the tools that will automatically be installed and configured, and it's very easy to go and add new tools through the command line. You can update all tools by just going and running cup all in this box starter shell, and you can see it'll go through and update everything. There's a lot of packages here that you can just easily be installed through the command line. So I highly recommend checking this out if you prefer doing things through Windows, or if you do a mix of both. Typically, if you're doing CTFs, you'll at least be working with, quite often, Windows executables. You might have some macros to analyze and things like that, and you'll want to do it in with some dynamic analysis. So it's great for that. I believe that there might be a similar setup actually specifically for malware analysis as well. This is the tools on this are more specific for pen testing, but this is what I've just set up, and I've gone and added some malware analysis tools on there for doing CTF stuff as well. So we will have a look at the IDA Pro disassembly of Split 32. So IDA Pro is a very popular disassembler and used for reverse engineering. Some alternatives would be Ghidra, which was released and open source by the NSA, and Binary Ninja, among others, but this is a popular one. So when we open the binary in IDA Pro, we're taken straight to the main function, and we can see calls to other functions here. We can see a list of functions on the side. There are calls to pwnme, where it's going to actually ask us for the data. And we can see we have a useful function here, obviously named as a hint to us to check out. And this is where we have a call to system, and the bin ls command is pushed to find the cat flag.txt string. We can go in view substrings and have a look at the list of strings in a program. We can see bin cat flag.txt, and we can have a look at it there in the data section and have a look at the address. If we have the plugin, we can generate pseudocode of functions to make this a bit more readable. So this puts it nearly back into the original kind of C code. As we see here, we've got the puts commands. We can go to pwnme, and yep, printf. It's reading in some data from us. 96 bytes, and calling puts. And then if we go to the useful function, this is literally just returning system bin /ls. It's going to be up to us to replace this with the call to bin cat flag.txt. I'll quickly demonstrate this in Ghidra as well. Ghidra's not something I have a great amount of experience with myself. Let's create a new project. Split. And then if we import file, split 32. Okay. So we're getting some information about the executable. And then let's try and double click it. To open up the code browser. It's not been analyzed, would you like to? Sure, let's analyze it. Just leave that at the default. And okay, so we have a list of our imports, exports. There's our useful string. Bin cat flag.txt. We have our functions here. Go to main. Okay, and then that's disassembled, that's decompiled that for us as well. So we have main pwnme. This just disassembles pwnme. So that's a nice layout. I will return to Ghidra in a later episode to hopefully demonstrate some more features when I have a bit more time. Okay, and let's return to our Parrot OS to find the offset of the instruction pointer. Okay, so now we're going to find the instruction pointer offset with pwntools. So let's run gdb pwntools and split 32. And in here we can have a look at the function. So let's disassemble the useful function. And we can see here this was where we had the call to system, which is what we want to utilize. So we can actually use this address, or we could use this address. But let's also get the address of bin cat flag.txt. So let's set a breakpoint at main and run the application. And if we do search bin /cat, and we have the offset of this string. It's important that we did search bin /cat and not just search flag.txt, because it would give us the offset of that part of the string, and we obviously need the whole string. It does mean, however, that if you had bin cat benign.txt and then you had somewhere else something malicious.txt, you could potentially join those strings together to bincat malicious or bincat, something worth remembering. So we have this address which we'll need, and then we have the system address. We need to just find the offset to the instruction pointer. So as we've done before, we can generate a cyclic pattern of 100 bytes. Let's take a copy of it and continue the execution. We're already running the program. Paste that in, and we've crashed the application. We've overflown the EIP with LAAA. So let's search for LAAA, and we find that was 44 bytes in. So we had to write 44 bytes to the buffer before we were able to overwrite the return pointer. So as we've done before, we can use Python to print out the payload. So let's print a times 40 plus, and then we're going to want the address of the system function call and then the address of the bin cat flag.txt string. So the system address was here, and the bin cat flag.txt address is here. Now we've seen this address many other times. These addresses, whenever we were checking strings and disassembling in various applications. So I'm just showing that there's various ways that we can do this, and afterwards we'll show in pwntools how we can automate it so that we don't need to do this at all, as long as we know obviously that these functions are there or to look for them. So let's put this in little endian format, \x 1a \x 86 \x 04 \x 08. That was 44 A's we needed, sorry. And then \x 30 \x A0 \x 04 \x 08. And if we print that, some of these characters won't encode properly, so we need to print it to payload, and then we can run split 32 and pass in the payload, and there we have our flag. If we wanted to visualize this more here, we could set another breakpoint. Let's set a breakpoint at system, and let's run with payload. So we've got a breakpoint at main. Let's continue, and now we have a breakpoint at system, and you can see the system has been called, system function has been called, and if we look, okay, we can see here that the string bincat flag.txt is on the stack. And if we just hit continue there, we'll get the flag. Now that we've exploited that manually, we can have a look at some pwntools scripts to see how we could have made life a bit easier. So first of all, look at the pwntools debug script. Again, this is a template, so all this up here is just for if you want to run with parameters or run with GDB or something like that. And we load the executable and get the context so that we don't need to worry about the architecture and the bits, OS, etc. We run the application, we look for the system function, grab that address, we look for the bin cat string, grab that address, and then we're just printing those out just for our info. We generate a cyclic pattern like we did in GDB. We send that and we wait for the program to crash. We open up the core file and then we find where the correct offset was for the instruction pointer. And let's just run that just to see what we get. Okay, so it grabbed, as it did for our as we did for the manual example, it's got the same addresses there. It found system, it found the bin cat flag.txt address, and then it found that the correct offset was 44 bytes. So now that we've got all that information, it's just a case of putting the payload together. And in this example here, we've used fit to set the offset. So here, this is basically a dictionary where the key is the offset that we want to place the value at, and the value is the call to system, just overwriting the return pointer there, just with any 4 bytes, and then the bin cat flag.txt address, and then we just send that payload off and we get our flag. So let's try and run that, and we see that worked. It gave us a flag. Finally, we're going to look at the autopwn script. So this, we don't bother trying to find the offset here. Let's just assume that we found the offset manually, and we've said it's 44 bytes. And we're not looking for the system address either. We just look for the bin cat address, the bin cat string, should I say. Print out the location of that, and then this time we're going to create a ROP object. So this is a class which simplifies generation of ROP chains. So in this case, we just create a ROP object with passing the binary split 32, and then we call ROP.system and pass it the bin cat flag.txt address, and that's all that's needed. So just like the last example, we call fit here, and we say that we want to place the ROP chain, this ROP chain, ROP system, at this offset, which we specified here. We write that payload to a file, and then we send that off. So let's just print out let's say the ROP here. We create the ROP object with the elf. So let's run that and see the output we get. So if we run that, it gives a list of all the gadgets that it was able to extract. Loaded 10 cached gadgets. If we go back and we can dump this ROP, let's have a look. So the ROP that we created there, we said ROP.system and passed in the address, and it's basically just created this ROP chain for us. So it's the system address, the return address, which could be anything there. It's put BAAA because it doesn't matter. I put 0x0 in the example that we gave, and then just the string. So that's the very short, quick and easy way to do this. That wrote the payload to the file. So if we cut the payload, we can see there's the payload. If we wanted to as well, we could also have a look at the actual ROP chain itself. So the call in ROP.chain will just convert convert this into the raw byte format. And that's it for the 32-bit binary exploitation. So next we will move on to the 64-bit challenge, which will be slightly different in this case. Okay, we're going to open this straight up with GDB and try and find the offset. So we generate a cyclic pattern of 100 and run, paste that in. Okay, so we can see that this crashes. We don't get to see what's in the instruction pointer, so we can do cyclic -L for the 4 bytes at the end of the RBP, and that gives us 36. So we know the RIP is 4 bytes after that, which is at 40 bytes. So there's 40 bytes of padding needed before we can overwrite the return pointer. Our functions, so if we disassemble useful function, we have the call to system there, and we have the address. So let's make a copy of some of these addresses. So let's say system equals this address, and we want to search for our bin cat address again. We have the address here, so let's say bin cat equals, and we just want to pad that out as well. Okay, unlike the 32-bit application that we were dealing with, 64-bit applications work slightly differently. So previously, whenever the system function was called, it just grabbed the bin cat flag.txt string off the stack. So we were able to just place the system call onto over the instruction pointer, and then follow that with the command that we wanted on the stack. For the 64-bit application, it will actually require the parameter to be in the RDI register. So we need to get the bin cat flag.txt string from the stack into this register. And how can we do that? Well, we can look for an instruction that already exists in the application to pop a value from the stack to the RDI register. So we can use a tool called ROPER and put in ROPER-F file and split, and that will give us a list of the ROP gadgets in there and the addresses. We can run that again and do search, and we want to search for pop RDI. So here we can grab the address of that. You can see here pop RDI and then return. There's the address. So ROP gadget. And this would need to go onto the stack first. So we would inject the ROP gadget followed by the bin cat address, and that would ensure that whenever this is executed, it'll pop the bin cat address off the stack into the RDI register, and then it will move on to the system call, which will then grab that parameter which we've popped into the RDI register. Hopefully that makes sense. So I'm gonna try and create a payload manually for this. So if we print a times 40, as we worked out that offset already, and then plus, I'm going to want in here our ROP gadget plus our bin cat flag.txt address plus our system function address. So let me first of all, just to make this a little bit easier, \x00 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 \x00. I'm just going to grab that to paste in whenever we need to pad out the addresses. So the first address is a ROP gadget. You can see we're doing in reverse order because of the little endian. Just always mention that. C3 \x07 \x40 \x00, and then let's paste in the rest. So that's our ROP gadget, and then our bin cat address is \x60 \x10 \x60 \x00, and then let's paste in the padding. Oh, not padding, but the to make it a 64-bit address. And then our system call, so \x4b \x07 \x40 \x00, and let's paste that in. Okay, and we need to do that in with Python 2 if we're not putting parameters around it, which I always forget to on the command line. And let's paste this to or let's save that to the payload file, and let's try and run split with the payload. Okay, so it printed our flag. Got a segmentation fault, all as expected. If we go back here and try, let's set a breakpoint at system, and well, so p system. Let's delete the breakpoints. Let's grab this system address, and we'll break asterisk for the memory address. We're going to break that address. We're going to run it with payload, and if we run there, we can see that we have the call bin-cat flag.txt. It's been called successfully, and we have our RDI. So you can see here that the bin-cat flag.txt has been placed in our RDI, and that's where the system function here is calling it. Okay, so let's see how we could have automated that whole process in pwntools. Let's close some of this stuff down. So as previously, we'll open up the script first of all, which we use to identify the offset. So in this example, like in the 32-bit auto-pwn one there, we created a ROP object with the elf, and then we've used this find gadget function, which will return a gadget with the instructions we're looking for, and we'll just take the first instance of it. So this is identical to us simply using the ROPER tool manually in the command line, getting this address, and then setting that address to equal that. It's the exact same thing. Here we're just printing out some of the addresses. Again, we're searching the executable for the bin-cat flag.txt, and we are getting the system address. We generate our cyclic payload of 100 bytes, and we send that, crash the program, and then read the core file to see where our stack pointer is, and then we use cyclic find to get the RIP, the instruction pointer, and then we generate our payload. So let's, before actually generating the payload and sending this off, let's try and print this out and see how it looks. If we do Python pwntools debug, so we can see that, yep, it found that gadget at the address that we'd already done manually, the same bin-cat and the system function. Found those all. It found that the offset was 40 bytes. And using the information that it found, then we can go ahead and automate the payload creation, where here we are doing 40 times no operation instructions. We're putting in our pop RDI gadget and the bin-cat address, which will then be popped into the RDI, and then the system function, which is called. So let's just make sure that all works properly. And you can see that prints out the flag as well. Okay, let's have a look at the auto-pwn script. If we open up auto-pwn. So for this example, we're not trying to find the offset again. We just found that manually, and we put in the padding value. We find the bin cat address, similarly using the same function, elf.search. But the ROP chain, we're able to simplify much more here. So the ROP, we create the ROP object, and then we just call ROP system with the bin cat address, and that's all we need to do. We don't need to worry about the finding the pop RDI gadget or anything like that. If we want to just have a look at this to print this out, let's run the autopwn. So if we run that, we can see it works. This was our ROP chain. It loaded 14 gadgets. Let's have a look if we uncomment these print statements. So you can see that these were the gadgets that it found, that we could have some of which we could have utilized, and this was the ROP chain that we created. So this function here, these two lines, creating the ROP object and then calling ROP.system bin cat address, has gone ahead and found this gadget for us, pop RDI. It's put the string that we wanted, bincat flag.txt, into the RDI, and then it's called system, all without us needing to actually worry about the intricacies. So all of these scripts and files are available on my GitHub, which I've linked in the description. I hope you've enjoyed this. As I say, this is not completely my expertise. I'm kind of putting this up as I'm trying to work through some of the stuff myself. So if anybody with more experience than myself has any tips and anything that I may have missed or that they can input, or any questions or anything like that, feel free to leave in the comments. Alright, thank you, bye.